back with the basic project that probably won't show us.
Hello, my name is and today I'll present to you the credit risk segmentation from clear credit with predicted probability of default from statistical machine learning and deep learning perspective. This is a project made by me with the help mentor of Dr. Zhao. So the outline of this presentation goes that we first will introduce the problem and setup, and then we will then explain the data preprocessing, which also includes the data cleaning, feature engineering, also the pipeline building, but it's more of a heavily detailed, so we'll leave it up when we get there. And then we'll do the model building and the scorecard building as well, and then we'll talk about illusion and future work. So for our motivation of this problem is that pretty much when you work in the finance industry, the thing that they would like to model, or I say we have, because it's not a not part of the finance industry, but the thing that we would like to model or kind of assess would kind of be the concept of risk. And the concept of risk is the concept of it's kind of like the consequence of not modeling risk is that we kind of tend to lose something. In this case, will be money. And well, of course, this type of risk, just money is the easiest one to comprehend because a company and stuff like that, the most valuable asset is of course money. So here, more specifically, I want to focus more on the concept of banking, specifically loan defaults, because when you give a loan to a loanee or a borrower, if they default, then you're not able to gain the money that is lost. So therefore, we would like to assess or predict or model the probability that the person will default, and therefore we can assess the strategy plans and then create policies around it based on the data that we have learned. And more specifically, I kind of want to emphasize that this takes part, like the timing of when this will be modeled will be very important, because then it will like kind of think about what type of variables to use and what's considered leakage variables. And for here, I want to stress that the time point of interest will be the most quote-unquote recent time, because the data is from 2014 to 2018. And for here, I just use the current, but in actuality, it's just quite really the most recent quote-unquote time so possible. So that's very important to tell. And I also, not only do I want to model it, but I want to build a kind of like a product or something, like a kind of like a deliverable where it can be used for people with non-technical backgrounds in the finance industry, or like stakeholders, in other words, who don't have the technical background that it or we. And then the data is the same one as presented by Wayne. This is the full lending club model data set. Which, as I said before, is 2014 to 2018, but this one has the 2 million rows and then 142 columns. So I would like to first discuss the construction of deep learning variable, because it's very important. And the reason why is because I started looking at the loan status variable as the main interest of the independent variable. But as you can see here, it is comprised of 7 unique components or features. But I did not want to deal with it as a multimodal type problem, so I kind of had to map it to build it to a binary case to make it much more easier to kind of model and much more easier to work with. So therefore, there's a mapping, and it's basically just statuses that are kind of close related to loans, defaults, and then also like non-defaults, or like good standings, or however you want to say it. And here you can see that class 1, or good standing in this case, is 5 times more much more present than the default type of 0. And there's the actual values of it. And this indicates a clear class imbalance, and was kind of the biggest obstacle when it comes to modeling these type of problems. And we will see that I tried my best to kind of alleviate this issue or problem. So therefore, we group into 2 classes, the default is and anyways, pipeline creation, which is the very most important thing to do. So the pipeline creation, I typically, I know that the process is probably do EDA, and then you do the whole data cleaning and stuff. But I did something kind of somewhat different, where we kind of did everything all at once inside the pipeline. So therefore, I had to go to computer science like methods, using transforming classes where we would fit it's like a fit and transform type of functions that kind of did all the cleaning, the feature engineering, and everything that was needed. And the reason I wanted to do this is because to give an honest assessment of the model's performance. And this was because I cut the features into, or split the whole entire data set into 3 sections from a subsample of 200,000 because computation power was a very big limitation. But I cut it to 200,000, and I cut it into a training set, a validation set, and a test set. And for these type of transformers, the reasoning is because we fit on the training data, because if we fit on the full data, we get over optimistic results because we're using the whole entire data set information. So when we do the fitting, we do the fitting on the training set to gather information from the data set from the training. But then we use the information from the training set to transform the variables to our validation set and test set when it comes to, and so they can have a more honest assessment of the model performance. Because if we don't do so, I got a model that when I didn't do it, I got like a high 90 and stuff like that. Not like that. So yeah, so that's what we did. An example here would be, and I just wanted to focus on the numerical pipeline as an example, but you kind of get the gist of it once you get the first gist. So pretty much, the pipeline what it does is it does a sequential order of steps denoted by me or however I coded it. But the point is that they both kind of share similar kind of functions. The first function here, in the numerical pipeline example, is a missing value dropper, which basically means that it drops the values based on a certain basic threshold. Here, for example, it's 50 as a baseline. So what we do here is that we look at the numerical columns, and we drop the value, the columns that have 50% missing variables or more. And I did it on purpose, like I said, made a manual, so we just change it because we don't know if 50% is the accurate one. And then we also do segmentations using the median because of the 140 something columns. It is not realistic to go do independent exploratory analysis looking at each column. So we have to use methods that were robust and therefore use a robust statistic when it comes to outliers and to not check the normality. And it saves time, it's more practical, therefore I use median. But I also did an ad indicator as well because it kind of gives the model the signal that we have imputed this data and also to reduce the influence of the such imputed value and not have so much influence on the model performance. And we also have an outlier flagger, which also kind of gives the model signal again that there's an outlier present. And also a robust scalar, which is different from a standard scalar because instead of using the mean, computer mean, like I said, we were not able to assess the external numerical column. We used a robust scalar which focuses on the quantiles, or quartiles. And this together, we're building another pipeline called preprocessing, which is this is like the base pipeline, the most important one because it's kind of like used for model selection. And what we did here is I did another transformation called the correlation selector. And what it does is it basically just assesses 2 numerical columns and checks if they are correlated with each other linearly using Pearson linear correlation. But then I dropped the one that had the less mutual information compared to when it comes to the dependent variable, because I wanted to keep the one that was the most informative when it comes to predicting the dependent variable of interest. And I used a sampler, which we important, but right now it's just there. But fitting a baseline model and just kind of testing it. Like, I also did a feature engineering set, which it has all the feature the functions that did the cleaning and the manual featuring in the columns that would be of interest as well. But I noticed that building it, like the baseline model with everything building everything together, it would take 20 minutes for one fit. And that's an ideal case because that's the most honest way we can assess the model. And we had everything just in the pipeline. But realistically, because it took 20 minutes to do one fit, I just did the feature engineering on the whole entire data set. And therefore, we used the training validation test set with the feature engineering already there because of practical limitations. And this is kind of like a visualization of like why the reason why we use robust scalar. And this is kind of what I kind of use for the pre-processing of the numerical columns only because, as you can tell, if you use the whole entire the training set with all the categorical variables, you get so much, it's like so much high cardinality when we're preprocessing. Using TNC, I use to assess like the, it kind of helps me choose the preprocessing steps, because this is what happens when you use a standard scalar. So we use visual component analysis to extract the most important data points, explain the most variability, and then use TNC to plot a high-dimensional data into a 2D kind of plot, and kind of see like our data at a global scale and assess like the behavior of the data. Here we use the standard scalar, whereas here we can see the segmentation, or I say segmentation, there's no segmentation in the classes because I did set too much noise. So I kind of, what I mean by that is that I kind of was focused more on the shape, on a distinct shape of like clusters. So here we have these two, but it's not really that like very obvious. But that's just the standard scalar. But here we use robust scalar, and here we can see in more kind of clusters that can kind of help us kind of like, like help to model, like ease it, and so kind of like reduce the noise. That will be something like this and that. Be able to make more accurate predictions. So the pipeline, there's another pipeline archetype because it's very important, because the sampler one that was noted first was because we decided to use sampling methods to address the class imbalance. Specifically, there was 3 that I had in mind. The random oversampler to oversample the minority class, undersample, and then undersampler to undersample the majority, and then smoke to create synthetic data set to kind of augment the lower class. And that is kind of one of the archetypes. The second archetype would be that for the machine learning and logistic regression, because that's the model I use, but we'll introduce it later. But the model I use, this is where I used kind of different model weights kind of to kind of put it to the minority. And then the third archetype, it's not really a picture here because it's a combination of both of them. But we find out that using both of them at the same time aggressively attacks the minority class, and it gives very, very poor generalization. So therefore, it's just a third option, just for the sake of completeness, but these are like the main ones that were kind of the ones to address the imbalance. So project phase model training and selection. So what I did is that I did a random search, because choosing hyperparameters is something that is time consuming if I did it by hand. So what I did is that what I did is that random search for like the most important, or the most like the hyperparameters that most affect the model, but also address the class imbalance, like the main targets of my hyperparameter training. So conducting a random search, which they do like a random combination per each iteration, but pretty much just like choose like a random like subset, but also then kind of evaluates how good it is with a validation set, because to do the model selection, train on the training, but then for here, for the model selection, and hyper-tuning, we use validation. So we conducted a randomized search with 10 random combinations and 3 cross validations. So that's where we cut the training data in 3, then use 2 to train the data, to train the model, use 1 for the evaluation. And we use that and on all these models to have a very fair assessment of all of them. And yeah, the models of interest were XGBoost classifier, where we start off with a small tree and keep boosting to augment the tree's performance until the noise becomes random to it. And then logistic regression kind of used to model kind of do like a little linear type of ways they classify. It's more of a classification, to probabilities. It's it will become very useful when it comes to constructing the scorecard because of its coefficients in the formula it has. So, and also a neural network and random forest. And just to be more explicit, logistic regression is the statistical type of model. Like we send them as a champion, and then like how a champion, and then we'll do like the random forest. Actually boost as the champion of machine learning, and then neural networks is deep learning. Oh wait, actually, yes. So I forgot to say, yeah, these are the results of the best performing type of models, and we'll talk more in depth about which kind of like sampling, combinations. But yeah, these are the results of the best performing ones for each type of It doesn't say like which samples they use or anything, but not able to check when they do it. This one. They're like the best ones that we use. So this is the one that the validation set, and this is the test set. So this is why we have 3 over here, because I chose the best from each type of class: the statistics, machine learning, and deep learning. And you just choose the best one out of all 3. So deep learning here was a bit more different than normal because this required a lot more manual kind of tuning and kind of thinking about what to do. The Python was very different. Everything is very different. So I decided to do a large neural network. Well, I did a large one, a medium, and a small. But the architecture type was very difficult because there was a bunch of combinations. And my original kind of model, architecture, was start off small, big, and then until we have a dense network there, and then we just start small. But it wasn't really practical, mainly because they drowned out too much noise, not too much enough information was going through the beginning. So I started a very dense kind of starting later and then go small. And they captured a lot of information, a lot more better. So there it is, you know, everything there, and then it's just I'm not going to do the manual stuff like that. So it's like put it here. So literally I use an add-on optimizer because I'm not going to have a consistent number, right? So I just did what is adaptive, more adaptive. And it looks back in the previous gradients, and I kind of did it myself. So that was really good. And the weight decay was also used to kind of do a regularization on to prevent overfitting because it penalizes larger weights. Okay, so yeah, that's a form of to reduce overfitting. Yeah. I'm sorry. But and then we have and then we also have drop to also reduce overfitting as well. And these are the parameter types, but the Python is more different because kind of neural networks kind of already does a bunch of model selection kind of by itself by reducing the reduction of weights. So then you really need to do a bunch of that, and it's much more easier to get there too in that aspect, I guess. So the selected models. These are the models I presented in the previous slide. These are the kind of the best hyperparameters and the best kind of combinations or hyperparameters chosen from the set, from the random set. And kind of also for today, I also did like a version of L1 and L2 type of regularization. There it is, all of this there. It's really not important for the concept of this thing, but for this presentation. But now that I kind of showed you how the model parameters are, but for now to build the scorecard, I use logistic regression because of its coefficients and kind of a sense like the size of the coefficient by itself kind of already kind of says how, the importance of it. So using those, we build the scorecard. And the scorecard, what it does is that it bends the important coefficients into kind of more, it bends the values and kind of assesses, like, depending on what the value, how much does it kind of affect, the rates of, or the rate of the event of having the defaults. And also how much using the kind of a scoring where we kind of just add up points and just do the whole entire summary. So that's what I did, but for logistic regression, I used the top 10 features for interpretability and just make it more easier to have. I didn't really buy it, but I did do a little row thing. But for neural network energy boosters, they don't have to do the chain parameterization. I just did the probability of default type of just regular just binning, and based on the output of the probabilities, it follows. That's how we assess the risk assessment. For example, these are the variables, the top 10 variables for logistic regression, and this is kind of an example of the scorecard that we get. And this is kind of what I wrote for a report for other class. So to quote example, this was an example of how the scorecard interprets one big variable. So rank principal loans with values below 1,996 or 59. We had an event rate of 0.73, meaning about 1.3% of loans in the group for default risk points. Since that event has a higher event rate, considered higher risk or receives negative score points. Which, of course, depending on the values that our customer has, we just add the score points. And as I said before, these are the bids that are created based on the probability of the output for neural networks and then XGBoost. And here is the kind of data frame that I kind of created to kind of show 50%, show 50% the sample, these are the index of the data, and this is the actual null status or the dependent variable. The probability output for the neural network, and also if it's a low or high risk. So conducting so kind of testing the scorecard for this regression, we obtain very results. And this is because I used this package called Optibitting, which kind of the scorecard for me. It's kind of like the same way as the transformer, where it kind of fits and transforms, and it assesses the scorecard metrics for you. So these are the results of the scorecard for this regression. I'm testing it. Limitations, I stated before, computational limitations was where I was not able to kind of explore a lot of things or further things because I was too stuck in the computational kind of thing, just like getting a computer running for the whole entire night and stuff like that. So that happens one of them. Like I said, the full like the full truthful pipeline where it has like everything all in the one pipeline is what I need to do. So kind of got rid of it, and that part of it is training the full data set. Take transform and then got 4 minutes. It was not the most 100% honest thing, but it is where it is. Future work. I think the most practical one that I see that is used in real life was do the default risk at our loan origination. That is very important because for business it's more important to kind of assess it before they receive the loan. So then that would require a whole entire new modeling procedure, where we have to get more into consideration leakage variables and just to not give out the information to the model and not be over predictive with information. In conclusion, logistic regression is actually like the best overall model. I would just say for interpretability. Like even though it is slightly below neural network in terms of order of general, I would say it's like it's the best simply because of the scorecard with it also because of the coefficients and kind of like I should have done something like landing really good. Like so that's the project. That should have done that. Now I know. The more you know. Give your audience space for yourself. Yeah, good.
Well.
Why are you so very fast?
Yeah, but a lot of work done, sorry. I like it. You did a lot, but this work is not to replace the work that the others were doing when we zoom into the logistic regression, right? After you selected the variables, you could visually see there were potential correlations in respect. Like the verification source, the verification status, the home ownership versus their. There were quite a few things that were just naturally correlated. We probably still need to check those, like how to tweak further from there.
Yes.
I see this whole process is a great modeling exercise, but its best power, I think, is one variable selection. But then you still need to apply another layer of.
Yes, I understand. Reading,
But that's another project.
I managed project much more better in that sense that it was. Now I know it was the next project to kind of focus more on logistic regression and more interpretation. You know, statistical being a very elegant type of just look at it, full model system and stuff like that. That's good.
Good job.
Any other questions?
Yeah. Can I go to the logistic regression model variable selection part? We see a lot of like variables similar with the findings work as well. So I think that's interesting, like the home ownership something, and also the interest rate something. I think we usually use natural language to summarize these variables because the prediction name is. I can understand some, but I can understand some, but I think you should list some kind of important variables using natural language instead of just the variable name.
I was a bit confused with that. Like I had like quite a bit of like squares there, just for like they have the whole entire dictionary where like it has like the variable and what it means. So I didn't touch it because I mean it was really for me because I do presentation should be much more like that. Yeah, so like they already have me build multi-different dictionaries. I have it. So you guys are presentation makes more sense. But yes, thank you.
You wanna honor your special guest?
Oh yes, yes. My sister is here.
Oh,
And
yeah.
his comments were very informative. I learned a lot. And I don't know if you guys noticed, but I had a lot of too much from it, I guess.
What's your name, I guess?
Yeah.